Hello everyone and welcome to the coronavirus edition of the sixth exercise from our signal theory class. In this exercise we will practice time-continuous systems described by an ordinary differential equation with constant coefficients. In this exercise we will deal only with homogeneous systems, that is the systems that do not have any external inputs. Those non-homogeneous systems, that is the systems with external inputs, we will deal with on the next lecture and next exercise. On this exercise I will start with a simple mechanical system which will be very easy to understand intuitively, and then I will move on to an electrical circuit. A simple mechanical system that I will start with is this pendulum. This pendulum has length L, mass m, and its angle is denoted as phi. The gravity force acting on the pendulum I have denoted as F sub g. This gravity force I can decompose into these two components. This component does not really affect the pendulum, only this one does. So to describe the movement of the pendulum I need to be able to express this force. To do that I need to realize that this angle is the same as this angle, and that means that I can describe this force, I can express this force as the gravity force times the sine of angle phi, the sine of this angle. This minus comes from the fact that the orientation of this force is opposite to the orientation of this angle. In addition to this component, which comes from the gravity acting on the pendulum, I have also added this second component, which is supposed to express the resistive force that the pendulum during its motion encounters. So this would be some resistance of the medium in which the pendulum is in. Typically this would be air, but you can have pendulum in water as well. The resistive force I model in this very simple manner, where I make it proportional to the angular velocity, and this c is the constant of proportionality. So this c is some coefficient of resistance, and again I have minus sign here because the resistance is acting against the movement of the pendulum, against the velocity of the pendulum. On the lecture we had a ball on a spring which was a linear motion, and in the linear motion we used these equations. So the acceleration, the linear acceleration, was given by the force divided by the mass, the velocity and its derivative was equal to the acceleration, and derivative of the position was equal to velocity. This was valid for linear motion, that is for the ball on the spring. This is not a linear motion, this is a circular motion. So I will need to use equation like these, but adjust it for a circular motion. And this is what I need to use. Here instead of acceleration I have angular acceleration, which is given by the moment of force divided by the moment of inertia. Then I have angular velocity, derivative of which is equal to the angular acceleration, and I have angle, derivative of which is equal to angular velocity. Now I need to express the moment of force, which is the force times the length of the pendulum, and moment of inertia, which, if I approximate this ball by a point, is given by mass times the length of the pendulum squared. Now I need to substitute for this force, so I will substitute this here. When I substitute, instead of this gravity force, I can write that the gravity is equal to the mass of the pendulum times the gravitational acceleration. And although when I substitute, I can change this angular velocity, and instead I can write that it is the derivative of the angle. Now to solve these equations I need to continue substituting. I can take this equation and substitute it into this one, and that will give me that the second derivative of my angle is equal to the angular acceleration. And now I will substitute for the angular acceleration, I will substitute this. Before I substitute, I will just take this term and divide it by this denominator, and I will take this term and also divide it by this denominator, and that will give me this. Now this left hand side and this right hand side actually give me a differential equation which describe the movement of the pendulum. But even though this is an ordinary differential equation, this is not an ordinary differential equation with constant coefficients. In an ordinary differential equation with constant coefficients, I would have my function, its derivatives, which would be multiplied by some constants, and then everything would be summed together. Here, I'm not just multiplying my function by some constant, I'm actually computing a sign of my function. So this is not an ordinary differential equation with constant coefficient. That means that you cannot use that simple approach that I showed you during the lecture to solve this equation. In fact, this differential equation is not even possible to solve analytically. But you can make an approximation which will turn this differential equation into an ordinary differential equation with constant coefficients, and that you will be able to solve. The approximation that you need to do is that you need to approximate this sine of phi with the phi itself. Turns out that if your angle is very small, the sine of your angle can be approximated by the angle itself. You can see that in the vicinity of 0, my angle and my sine of angle are very close. So I can approximate this sine of phi with phi itself, which I have done here, and that gave me this differential equation with constant coefficients. Now you can see that I have only my function, its derivative, those derivatives are multiplied by constants, and everything is summed or subtracted together. Now to put this differential equation into that standard form which I showed you during the lecture, I can take these terms which contain my function and move them to the left hand side. That is what I have done here, and this is my differential equation which I'm going to solve. From the lecture, you will be looking for the solution in this form. Now you will take this solution and you will substitute it into this differential equation. You will get this. Then you will need to evaluate these derivatives. When you do, you will get this. In here, you will note that you can cancel out these a's and you can cancel out these exponentials. And when you do, you will get your characteristic equation. At this point, you might note that these two steps are a little bit redundant. I mean, each and every time we substitute this solution, each and every time we take these derivatives, which give me the same result each and every time. I mean, each and every time, if I have second derivative here, I'm going to end up with lambda squared here. If I have the first derivative here, I'm going to end up with lambda. If I do not have any derivative, well, this just does not change. So in general, the nth derivative will just give me lambda to the power of n. And then each and every time I will cancel out these a's and these exponentials. So if you can see this, you can actually save yourself some trouble, and you can note that your characteristic equation can be actually obtained directly from your differential equation. You can see that your characteristic equation is very similar to that differential equation. Instead of the nth derivative of your function, you have lambda to the power of n. Now that I have constructed my characteristic equation, I can proceed to solve my differential equation for different values of these constants. In each case, I will use these initial conditions. The initial angle of the pendulum will be 0, and the initial angular velocity of the pendulum will be 1/2. This is my first case. Here I have set the coefficient of resistance to be 0, so I live in an ideal world where I have no resistance. The mass of the pendulum is 1 and the length of the pendulum is 2.5. The gravitational acceleration is 10, so I'm on Earth. Now when I take these constants and I substitute them into my characteristic equation, I will get this. From this characteristic equation, I can find that the roots of the characteristic equation are plus minus 2j. I can plot this into the complex plane, and from here I can immediately see that I'm dealing with a marginally stable case, so my solution will be undamped oscillations. Because my roots are complex, it is convenient to look for the general solution in this form. my roots have 0 real part and the imaginary part is plus minus 2j. So my sigma is 0 and my omega is 2. When I take these values and I substitute them into the general solution, this exponential will be equal to 1. And for omega I will substitute 2. That will give me this. So this is the general solution which shows all the possible ways how my pendulum can move. But I'm interested in the very specific movement of the pendulum which is initiated by these initial conditions. So now I will be looking for the particular solution for the initial angle 0 and the initial angular velocity 1/2. I have that here. First I need to express what is this general solution at time 0. So I will substitute 0 for time here and here. That will just give me this coefficient C1. I have that written here, and from that initial condition I have said that this should be 0, which gives me that coefficient C1 is equal to 0. Now that second initial condition that says that derivative at time 0 should be 1/2. So at first I need to express the derivative of the general solution. So I need to take derivative of this, which will give me this. Now I will substitute time 0, and also I will use the fact that C1 is equal to 0, and that will give me this. And as per that initial condition, this is supposed to be equal 1/2, from where I can get that my coefficient C2 is 1/4. So I take these two coefficients, substitute them into the general solution, and that will give me this particular solution. So this is how my pendulum will move for these initial conditions. Here I have it plotted. And you can see that I'm getting undamped oscillations. So my pendulum will go back and forth indefinitely. In this case, I have made my pendulum a little bit more realistic. I have set my coefficient of friction to be equal to 2, so now I do have some friction, and intuitively you understand that now the pendulum cannot oscillate indefinitely. Eventually it has to slow down and asymptotically approach 0. I have also set the mass to be 1, the length of the pendulum is 1, and I'm still on Earth, so that gravitational acceleration is 10. When I use these constants and substitute them into that characteristic equation, I will get this characteristic equation. To solve this characteristic equation and find its roots, I need to compute the discriminant, which in case is -36. With that, I can compute those roots of the characteristic equation. This is the formula, and when you evaluate it, you will get that the roots are -1 plus minus 3j. I can take these roots and plot them into the complex plane, and here I immediately see that the system will be stable because those roots are on the left hand side of the complex plane, and because they are complex, the response of the system will be stable underdamped. When I have complex roots, it is convenient to use this form of the general solution where I have already substituted for sigma and omega. Here you can see that your sigma is -1 and your omega is 3. So you get this general solution. And this general solution gives me all the possible ways how the system can behave. But in this case, I'm not interested in all the possible ways how the system can behave. I want to know how my system will behave for my specific initial conditions, these initial conditions. I will start with the first initial condition, so I will need to express what the angle of pendulum is at time 0. So I need to substitute 0 into this general solution. When I do that, I will get this, which will simplify into C1, and as per that first initial condition, this is supposed to be equal to 0. So C1 must be 0. Now the second initial condition. For that, I first need to compute derivative of my angle. So that means that I need to compute derivative of my general solution. And when I do, I will get this. Now that I have that derivative, I can substitute 0 for time. So I will substitute 0 here, 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 and here. When I do that, I will get this expression. And when I evaluate this expression and also use the fact that I already know that C1 is 0, I will get that this long expression is just 3C2. And per the second initial condition, this is supposed to be equal to 1 over 2, from where I can get that C2 must be 1 over 6. Now I will use these constants and substitute them into my general solution, and I will get my particular solution. So this will be the specific way how my system will behave for my specific initial conditions. Here I have it plotted. So you can see that my pendulum will swing on one side, then a little bit on the other side, and then with this swinging motion it will asymptotically approach 0. So I will have stable underdamped response. In this case, I have almost the same setup as on the previous slide, except I have increased this coefficient of resistance to 7. So now I have more resistance that is slowing my pendulum down. When I use these constants and I substitute them into the characteristic equation will have this form. Now to solve it and to find its roots, I will need to find the discriminant, which in this case is 9, and the individual roots, when you crunch it, will be -5 and -2. When I plot them into the complex plane, they will lie on the real axis on the left hand side of the complex plane. So my system will be stable, and because my roots are real, the response will be overdamped. I should not have any oscillations in the response of the system. Because the roots are real, I can use this form of the general solution where I have already substituted those roots for lambdas. So this is the general solution which will give me all the ways how my system can behave. Now to find a particular solution for my specific initial conditions, I will need to express this general solution at time 0. When I substitute 0 for time, I get this, which will simplify into this. And this, per the first initial condition, is supposed to be equal to 0. Now to use the second initial condition, I will first need to express derivative of my angle, that is derivative of this general solution, which I have done here. And now I can substitute 0 for time. 0 for this time, I have done that here. And this simplifies into this, which per second initial condition is supposed to be equal to 1 over 2. So now I have this system of these two equations, which I need to solve to get my constants a1 and a2. Let's do that. From this first equation, I get that a1 is equal to minus a2. This I can substitute to this second equation, which will give me this equation. And from there, I can write that a2 is 1 over 6. And from here, I can write that a1 is minus 1 over 6. So now I can take these constants, substitute them into the general solution, and that will give me my particular solution. This is how my system will behave for my initial conditions. I have plotted that here. I have actually plotted both of these exponentials separately. So this first exponential is plotted as this blue line here, and the second exponential is plotted as this green line here. When you sum them up, you get this black line, and that is the response of my system for these initial conditions. So in this case, I do not have any oscillations. This is overdamped response. So my pendulum will just swing to one side, and then it will exponentially come to 0. In this case, I will turn the pendulum upside down. I will turn it into the inverse pendulum. The inverse pendulum can be described pretty much the same way as the normal pendulum, well, except it is upside down. When you crunch the physics, you will get that the inverse pendulum can be described using this differential equation, which has this characteristic equation. Now let's solve the movement of this characteristic equation for these constants. The coefficient of friction I will set to 3, the mass I will set to 1, the length of the pendulum will be 1, and the gravity acceleration will be 10, so I'm still on Earth. In this case, with these constants, the characteristic equation will become this. The discriminant of this characteristic equation will be 49, and when you crunch the math, you can find that the roots of the characteristic equation are -5 and +2. When I plot them into the complex plane, I can see that one of the roots moved to the right-hand side of the complex plane. That means that my system will be unstable. Because my roots are real, I can write the general solution of my differential equation in this form. Here I have already substituted for the lambdas. This -5 came here, this +2 came here. In this general solution, you can already see that this is the exponential which is responsible for my system being unstable. This is the exponential which is rising to infinity because I have a positive number here, because I have this number 2, this number 2, this number 2, which is on the right hand side of the complex plane, which is making my system unstable. So this is my general solution, and now let's compute the particular solution for these initial conditions. My initial angle will be 0, and my initial derivative of the angle, that is the angular velocity, will be 1. I will start with this first initial condition, and I will express this general solution at time 0, which is this, which simplifies into this. And per this first initial condition, it is supposed to be equal to 0. Now I will use this second initial condition. For that I will need to express derivative of my general solution. So I will take derivative of this, and that will give me this. Now I will compute that derivative at time 0. So I will substitute 0 here, and that will give me this, which will simplify into this, which per this initial condition is supposed to be equal to 1. Now I have these two equations which I will use to compute A1 and A2. From this first equation I will express that A1 is equal to minus A2. That I will substitute to this second equation, which will give me this equation, and from there I can compute that A2 is 1/7. And when I substitute that here, I will get that A1 is minus 1/7. And when I get these constants and I substitute them into the general solution, I will get my particular solution for these initial conditions. So this is how my inverse pendulum will behave. When I plot it, I will get this. You can see that the pendulum will not become stable at 0, but it will fall to one side. Just a side note, when you derive this differential equation, you need to use that approximation that sine of phi is approximately phi, and that is valid only for small phi. So our solution is also valid only for small phi. When you take a look at it, you cannot expect that our pendulum, the angle of our pendulum, will rise indefinitely. That would essentially mean that your pendulum will start to rotate like this. No, our solution is valid only for a small angle phi, and then the real pendulum will behave differently from what we computed. Okay, so on the previous slides we did the pendulum and the inverse pendulum, which were nicely intuitive. But you are not to become pendulum engineers, you are to become electrical engineers. So let's do an electrical circuit. Here I have a simple RLC circuit, and in this circuit I would like to find out what is the voltage of my capacitor when I said that the initial voltage of the capacitor at time 0 is 1 volt and the initial current in the circuit, that is this current, at time 0 is 0 amps. The values of the individual elements are these. This is the resistance, inductance, and capacitance of this resistor, inductor, and capacitor. Now to solve this circuit, I need to describe this with a differential equation using a basic circuit theory. So, the voltage on the capacitor must be equal to the voltage on the resistor plus the voltage on the inductor. I have written that here. The voltage on the resistor I can express as this current times the resistance that I have written here. The voltage on the inductor I can express as derivative of this current times the inductance. The last thing that I need to use is that the current through this capacitor is equal to the derivative of the voltage on the capacitor times the capacitance. This minus sign is here because the orientation of my voltage is opposite to the orientation of my current. Okay, and now I can take this equation and substitute it into this one, which will give me this equation. Now I will move these terms with my unknown function to the left hand side so that I will get the standard form which we used on the lecture. Now to solve this, if I do it the long way, I can write down that I expect the solution to be in this form. I will substitute this into my differential equation. I will get this, then I will evaluate the derivatives, and that will give me this. Here I will cancel a's and exponentials, a's, exponentials, a's, exponentials, and that will give me my characteristic equation. Or if you are already tired of this, you can just take a look at the differential equation and you can directly write LC here. Instead of the second derivative, I will write lambda squared plus RC. Instead of the first derivative, I will write lambda plus, here I do not have any derivative, so I will just write this coefficient, which is 1 times lambda to the power of 0, which is 1. And that will give me this characteristic equation. Now I will substitute into this characteristic equation and I will substitute these values. That will give me this, which I can simplify into this. So this will be my characteristic equation for these values. So to solve this characteristic equation, I need to find the discriminant, which is this. And when you crunch the numbers, you will find that the discriminant is minus 9 times 10 to the power of minus 4. When you have your discriminant, you can compute the roots of the characteristic equation. And again, you need to evaluate this formula. And when you do, you will get that your roots are minus 20 plus minus j60. When you plot those into the complex plane, I can see that they lie on the left-hand side of the complex plane, which means that my system is stable and they are complex. They have non-zero imaginary part, which means that the response will be underdamped. When I have my roots complex, it is convenient to use this form of the general solution. Before, we always used constants C1 and C2 here, but I have already used C for the capacitance. So just not to make this even more messier, I will stick with A1 and A2 here. Now I will substitute for sigma and omega. My sigma is minus 20 and omega is 60. Here I have it substituted. This is my general solution. That is all the way how my system can behave. Now let's compute the particular solution for these initial conditions. I will use this initial condition first. So I will express my general solution at time 0. I will substitute 0 here, here, and here. And I will get this, which simplifies into this, which is supposed to be equal to 1 as per this initial condition. And from there I will get that my constant A1 is 1. Now let's use this second initial condition. Here it is a little tricky. Where do I get this current? Well, I have my general solution for the voltage, but the initial condition is specified for the current. This is very simple. I just need to compute the current from the voltage. How do I do that? We actually mentioned that here. The connection between the voltage and the current on the capacitor is this. I need to take derivative of the voltage multiplied by the capacitance, take the minus sign, and that will give me the current. So I will need to use this connection which tells me that I need to evaluate derivative of my general solution. I have done that here, actually in general, for general sigma and omega, and then I substitute for sigma, omega, A1, and I will also substitute that the time is 0, and that will give me this. And from there I can compute that my coefficient A2 is 1/3. Now I have my constants A1 and A2. I will substitute them into this general solution, and that will give me my particular solution for these initial conditions. So this is how my voltage on this capacitor will behave. Here I have it plotted, and you can see that I have that underdamped response and the system is stable. So with this oscillatory motion, that voltage on the capacitor will asymptotically approach 0. What is going on physically? At the beginning, I have some voltage on this capacitor and no current is yet flowing in the circuit. So there is some charge, some energy in this capacitor, and that will start to flow through this resistor into this inductor. And that is basically what is going on here. As that current is flowing from that capacitor to these other parts of the circuit, this capacitor discharges itself, and you can see that the voltage on the capacitor is falling down. Now, as this current is flowing through this inductor, that inductor is storing the energy of that current into its magnetic field. So as that capacitor discharges itself to 0, that energy stored in the magnetic field of this inductor will keep the current flowing, and it will start to charge this capacitor again, but to negative voltage. At some moment, the energy stored in the magnetic field of this inductor will dissipate and this capacitor will no longer be charged. That is this point. The voltage on the capacitor is no longer increasing to negative values. So now we have capacitor charged to some negative voltage, and basically the entire process repeats itself. The capacitor will start to discharge, except now with opposite sign of the current. Some energy is being transferred into the magnetic field of the inductor, which will keep the current flowing, and then it will charge this capacitor to opposite voltage. But in every cycle of this energy exchange, some energy is dissipated on this resistor, and that is why we have this exponential damping here, and that is why the amplitude of these oscillations is decreasing and the voltage on the capacitor is asymptotically approaching 0. On this slide, I have a small variation of the circuit from the previous slide. Everything is the same, the circuit is actually the same. The only thing that I have changed is the value of resistance. On the previous slide, I had the resistance of 1 ohm. Now my resistance is square root of 10 ohms. The circuit is the same, so this derivation is the same. I will not go over it again. When I substitute these values into my characteristic equation, I get this. It's the same as on the previous slide, except now instead of number 1, which was the value of the resistor here, I have square root of 10. When I crunch these numbers, I can rewrite that characteristic equation into this simpler form, and then I can solve it. Discriminant of this characteristic equation turns out to be 0. And when I compute the roots of the characteristic equation, I will crunch this formula, I will get that my characteristic equation has only one double root. When I plot it into the complex plane, I get this. By the way, this is an alternative way how you can express that this root is double. You use this double cross. So this is the special case where my discriminant is 0 and I have a single double root. In this case, the general solution has this form. Here I have already substituted for lambda, and in this case I must not forget that the second exponential is multiplied by t. So I have this small change, but the rest uses the same principle as before. This is my general solution, so this tells me all the ways how my system can behave. And now I want to find my particular solution using these initial conditions. So I will start with this initial condition. I will express the general solution at time 0, which, when I substitute 0 here, gives me this, and that simplifies into this, and per this initial condition, this is supposed to be 1. So from here I get that A1 is equal to 1. Now I need to use the second initial condition, so I need to express the current, I need to evaluate this derivative of my general solution, and that I have done here. Now I need to express that current at 0 time, which means that I need to express the derivative at 0 time. I need to substitute 0 here and here, which I have done here. And when you crunch this, it will actually simplify into this. Here I can use that A1 is equal to 1, and from this equation I will then get that A2 is 20 times square root of 10. Now I can use these constants, substitute them into the general solution, and that will give me my particular solution for these initial conditions. This particular solution I have plotted here. These green and blue lines actually correspond to this first and this second exponential respectively. Now, what is the difference between the behavior of our circuit in this case, where my resistor is bigger, and the previous case where I had the resistor smaller? Well, in this case, because this resistor is bigger, when this capacitor is discharging, more of the energy is being dissipated on this resistor, so not that much energy is being stored in the magnetic field of this inductor, so this inductor does not have the strength to charge this capacitor to negative voltage. I do not have that overshoot, this overshoot which I had on the previous slide. Here the capacitor just quickly discharges and its voltage exponentially approaches 0. Here on this last slide, I have again just a small variation of the circuit from the previous slide. The circuit itself is the same, and the only thing that I have changed is the value of resistance. Now I have increased the resistance even more, and now it is 5.5 ohms. This description of the circuit and derivation of the differential equation and characteristic equation is still the same because the circuit is the same. Now I will take these values and I will substitute them into my characteristic equation. I will get this, which is again almost the same as before, except now for the resistance I have substituted 5.5. When I crunch these numbers, I will get this characteristic equation. Now to find the roots of this characteristic equation, I need to find the discriminant, and when I crunch all those formulas, I will get that the discriminant is 20.25. Now that I have the discriminant, I can find the roots of the characteristic equation. And again, when you crunch the numbers, you will get that your roots are -200 and -20. When I plot this in the complex plane, this is what I get. I get two real negative roots. The roots are on the left hand side of the complex plane, so my system is going to be stable. The roots are real, so I will have overdamped response. With two different roots, the general solution of my differential equation will have this form. I have already substituted for the lambdas. And now I will continue in the same manner as before. This is my general solution, so this describes all the behavior of my circuit. I want to have one behavior which starts with these initial conditions, so I will need to use those initial conditions. First, this one, I will express the general solution at time 0, which is this, which gives me this, and that is supposed to be equal to 1 because of this initial condition. The second initial condition, here I have my current, which is equal to this, so I need to compute derivative of my general solution, which I have done here, and now I need to express that at time 0, which I have done here. And when I crunch these numbers, I will get this. This equation can actually be simplified into this one. Now I have these two equations, and when I combine them, I can compute that these constants A1 and A2 are -1/9 and 10/9. Now I will take these constants, substitute them into the general solution, and that will give me this particular solution. This will describe how my voltage on my capacitor will change for these initial conditions. And I have plotted that here. Now you can see that the capacitor is discharging and its voltage is exponentially approaching zero. From the electrical standpoint, this math is telling me that when I increase this resistor, there will be smaller current flowing out of the capacitor and it will take longer time for the capacitor to discharge, at least in comparison with the previous case. In this case, my resistance is 5.5. In the previous case, my resistance was square root of 10, which is about 3.2. In this case where I had that critical damping, my capacitor was discharged to almost zero level at 100 milliseconds. In my last case, where my resistance is 5.5, the capacitor was discharged to almost zero level at more than 200 milliseconds. So this math is confirming kind of intuitive fact that when I decrease this resistance, then this capacitor will discharge faster. But if I overdo it and I make this resistance too small, that is what I had in that first case, when my resistor was 1 ohm, then I'm going to end up with this oscillatory response. If I do not want this oscillatory response, if I do not want this overshoot to negative values, and I do not want to wait for these oscillations to dissipate, then the smallest value of the resistor which I can get to this circuit and not to end up with oscillatory response is exactly this value, which gives me that critically damped response. If I make this resistance smaller, then I will get this case number 1 where I have oscillatory response. If I make this resistor bigger, then I will get my last case where I have that overdamped response which takes a long time to stabilize. That critically damped response lives in between these two and it gives me the fastest discharge, that is the fastest stabilization of my circuit.